Hello, 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 everybody. Root Beer here with question number 25 on the 2002 Pascal competition. So this is the last question on the competition here. A student has two open-topped cylindrical containers. The walls of the two containers are thin enough so their width can be ignored. Okay, good to know. The larger container has a height of 20 centimeters, just as we have pictured over here, and a radius of 6 centimeters, which isn't on the diagram at all, and contains water to a depth of 17 centimeters. The smaller container has a height of 18 centimeters, so this one up here, and the arrows seem to suggest it's going down. 18 centimeters, radius of 5 centimeters, and it's empty. No water or anything else in that. The student slowly lowers the smaller container into the larger container as shown in the cross-section of the cylinders in figure 1. As the smaller container is lowered, the water first it starts to move up and then it overflows out of the larger container. And that's what's happening in figure 2. And then when the smaller container is resting on the bottom of the larger container, and then eventually pours into the smaller container. When the smaller container is resting on the bottom of the larger container, the depth of the water in the smaller container will be closest to, and we have some answers, 2.82, 2.84, 2.86, 2.88, and 2.90 centimeters. So closest to, I'm immediately reaching for my calculator, because I know I'm probably going to have to perform a computation around it. And I'm making a prediction here. I don't do these questions ahead of time when I record them, unless I make like a major mistake and then I've half recorded one, so I've had half a practice for a question. But I haven't done that with 25. This is the first time I'm looking at 25 since I wrote the competition. But I'm making a prediction. I think the answer was 288, or maybe that's the answer I circled and got wrong. I know I only missed one question in Part C on this competition because I came back with a 142. And so I'm just calling it power of memory. It's been well over a decade, almost 2. Has it been 2 days? Anyway, but I'm calling it 288. We're going to see if that's right. Who knows? All right, so jumping back into it. So we've got figure 1 and figure 2, but it's not telling the whole story. So what I'm going to do is I'm actually going to draw some more figures, and I'm going to better understand what's happening. When does the water start pouring into the smaller container is my primary concern. What does that look like? So I think I'm going to need more than 3. So what I'm going to do is I'm going to write them across the top here. So we have our big container and it's got water in it. And we have this smaller one starting to lower into the picture. And the water's at a certain height. Then, eventually, the smaller one starts breaching the water. And the water level moves up around it. And then it finally reaches the top, starts flowing out. So at this point, the water level at the top is always going to remain constant, just the excess is going to keep flowing out. Okay? So then water keeps flowing out, and the smaller one keeps getting lowered in. Eventually, the top of the lower one and the top of the bigger one are going to be at the same height. Once again, the water is still going to be here. Having just finished flowing out, the water is not going to flow out anymore after this. And as we continue to lower it, because we still have a gap here of 2 centimeters, I believe. So we keep lowering it, and now the water starts gushing in. So all the excess water starts flowing in here, because there is excess water. And finally, the small container rests at the very bottom. And any water that was up above has flowed in, and so the water is resting perfectly level with this, so at 18 centimeters, and then there's some water that has flown in here. So this is in general what the picture looks like. So really it's 7 figures. No, sorry, 6 figures. Okay. So we want to know what this height is in the small container in the last one, in the last picture. Okay. So what are we to do? Well, I suppose they give us the information. They give us the information that some water starts flowing out. Now, if we didn't have that information, we might have a bit of a problem. Because if we didn't know the water flows out, it's possible that there's so little water that even when I put the smaller one in, it never actually reaches the height of 20 centimeters. But I'm told that the water flows out. So at this point, I'm really just concerned. I want to start here. How much water is left when it's all done flowing out and then starts to flow in? Because that's the total amount of water, the total volume of water I have to work with. Okay? And so this water amount should be the total 20 centimeters and 6 centimeters. So 20 centimeters high, 6 centimeters for the radius, minus the volume of air in this smaller cylinder, which is 5 centimeters of a radius and 18 centimeters high. So the volume of water once it's done flowing out. We are told that the water starts to flow out, so eventually we will reach this point, just as the smaller cylinder is at the same height as the top of the bigger cylinder. That's when the water is just going to stay on that level, and then it's going to start flowing in. So what's that volume of water? Well, what's the volume? It's the volume of one cylinder minus the volume. So volume big cylinder minus the volume of the small cylinder. Small cylinder is full of air, so it has no water to contribute. So the volume of the big one, what's the volume for a cylinder? That's pi r squared h. So in this case, it's going to be pi 6 squared and a height of 20 minus the volume of the small one, so that's a radius of 5 squared times 18. I'm going to take out a factor of pi here for a moment. I'm going to grab my calculator, because I'm going to need it later anyway. So 36 times 20, that's 720, minus 25 times 18, 440. So that's going to be pi times 270. So 270 pi. Okay. So the volume of water at the end is going to be 270 pi, and if we had to, we'd say centimeters cubed. So I'm going to go back and double check all my numbers before I proceed. 20 centimeters, 6 centimeters. I don't think I need this 17 centimeters, but we'll see at the end. Because I'm told that it flows out, so the 17 doesn't matter. Because eventually that's going to change, and all I care about is the water just before it starts flowing in to the little one. So the water just as it stops flowing out of the big one. Because all the water that flows out, I don't care about that. It's not going into the small one, so I don't really care how much of it there is. So 26, and then we have 18, 5. So it looks like all my numbers are correct so far. So once the water is done flowing out, the water only goes from the big cylinder into the small one. So in these last 3 pictures, there's the same amount of water, 270 pi centimeters cubed, in each picture. The only question is, how much water is in here in the small one? Well, how much water is left in the big cylinder? Okay. So 270 pi is the same as volume of water in the big one, different than volume of big one, minus the volume of water, or plus the volume of water in the small one. So I'm going to call these VB for V in big, and VS for V in small. So I want to know how much volume is in the small one, because once I know that, I know the radius, and there's a quick formula to turn this volume with the radius into the height. Just divide by pi, divide by the radius squared, suddenly you've got h, the height. So I want this amount. I think I can work out what this amount is. So this water is only up to a height of 18. So if we didn't have this cylinder here, the small cylinder, we'd have a cylinder of a column of water of height 18 and radius 6. But we do have this small cylinder, so he takes up space. So I think VB is going to be pi 6 squared times 18. Imagine that there were a column of water here, minus the volume of this smaller cylinder. 5 squared times 18. Never mind the water that's in here, we're just calculating how much water is outside. And the water fills up all the space that's outside. So really we're asking how much space is outside. So it's the difference of two cylinders of height 18. That's what we've got going on. So once again, we'll take out a pi. 36 times 18. Grabbing my calculator once again. So that's 648 minus, well, we already worked out 5 squared times 18. That's 450. So that's going to be pi times 198. So that tells me how much water is still in the big cylinder. So now I can rearrange and figure out how much water is in the small cylinder. So it has volume Vs, which is 270 pi, the total volume of water after it's all done flowing out, minus, I think it was 198. Let's just go back and double check. Yeah, 198 pi. Okay. And so that's going to be something pi. So 270 minus 198, that's going to be 72 pi. That's how much water is in the small cylinder, the small container. So that's going to be pi times the radius squared times height of water. And the height of water is what we wanted all along. So that's pi, it's 5 squared times the height of the water. So that's 72 pi. The pi's are going to cancel out. And we can rearrange this. We'll say the height of water is 72 over 5 squared, which is 25. So 72 divided by 25. That gives me an answer of exactly 2.88. Called it. I feel really good. I like it when my memory can remember really trivial nonsense from years and years ago. So that's my height, 2.88, and that'll be in centimeters. But I'm a little suspicious, just a little suspicious, because smallest container will be closest to, and I got it exactly on. So what I want to do is I'm just going to, just for a moment, I'm going to make sure water did actually flow out of the pipe. I think we've got our answer. I think it's D, 2.88, but I want to make sure water did flow out of the big one. So how do I do that? Well, I need to make sure that the starting volume is different than this 270 pi centimeters cubed, the volume that we get when the water stops flowing out. if 275 pi is bigger than the whatever this amount over here was with height 17 was, if 270 pi is bigger, then it means we somehow added water by water flowing out, and that doesn't make sense. But if this value, if the water we start with is more than 270 pi, that means water had to flow out to reach this stage. Okay, so I'm just going to quickly double check. So check that water flows out. So the volume that we start with must be bigger than 270 pi centimeters cubed. Well, the volume that we start with, that's pi 617, and that's going to be pi 36 times 17, and that's 612, so it's 612 pi. So you better believe water flowed out. In fact, we can tell you how much water flowed out. 342 pi centimeters cubed flowed out. That's not relevant to the actual question, but it does prove to me that water did flow out. Okay, so I'm happy with that. I'm going to erase those calculations and just leave this 2.88 right there. And that was an answer of D. Okay, so that concludes the entire 2002 Pascal competition. It's been quite a bit of a journey. And I don't really have a whole lot else to say. I liked that question. I'm glad that my memory is still working after all these years, because 2.88 jumped out at me as soon as I read it as I was warming up. So I really liked that, and I really liked the 2002 overall. I'd say all the questions were really nicely put together for the most part. One or two that maybe I wouldn't have put in, but that's always how it is. There's always, I mean, I don't design these competitions, so I don't really have the right to throw stones. But I think it was a very good question. I can't wait to see the 2002 Kaylee. Hopefully you're just as eager as I am. So you can click the link in the description, not only get this contest, if you're just joining me, but you can also get the 2002 Kaylee, and that's what I'm going to go to next. So, yeah, I'll see you guys then.